Hi everyone. In this video, I am going to explain about a problem called Travelling Salesperson Problem, and I am solving this Travelling Salesperson Problem by applying branch and bound technique. Okay. Now, in this video, I am going to cover what you mean by Travelling Salesperson Problem and what you mean by branch and bound technique. Okay. So this is another algorithm design technique. Okay, so what do you mean by what is this branch and bound technique? And I'm taking a simple example to explain how a traveling salesperson problem is solved by applying branch and bound technique. Suppose if you people are familiar with what you mean by traveling salesperson problem and branch and bound technique, you can skip these two and go directly to the example. Okay, now let us see first what do you mean by traveling salesperson problem. In this traveling salesperson problem, given there are n number of cities that we are representing as a graph. Okay, and then here the salesperson has to visit all these n number of cities exactly once, and he has to return to the starting city. That means he has to start from any one city arbitrarily. That means randomly we can select any one city. From that city we are starting, and then from that one city we need to visit all the cities exactly once, and we have to come back to the starting city. And here this is a problem statement, but here the constraint, the condition is we need to visit all the cities exactly once, okay, in such a way that all the cities should be covered in a shortest distance. That means the tour should be shortest. That's what the objective of this problem. Okay, so minimum distance. In the minimum distance, we have to cover all the cities. Now, let us take simple one example. Let us take some simple 4 cities A, B, C, D, and now these are connected like this. For example, okay, so this now for this problem, the given graph should be weighted, should be connected. Okay, so and then, so let us take a simple example. This is the one graph. Now assume I started from the vertex A. So you can start from any vertex. There is not a problem. Okay, not in the no conditions like that. We can start from any vertex. Assume if I start vertex A, then I can go to B or I can go to D, like that I can visit all the vertices in such a way that, and then I have to come back to the same starting city in a shortest distance. Now in this example, directly you can say, see these are the minimum values. Say if I starting from A I can go to what? C. Okay, A to go to C. Then from C to I can go to D. Then D to B, then B to A. So now the path is what? So this one. So A to C here, then from here, then from here. Same thing. I have started from A and I am ending at A. Okay, A to C, the cost is 1, 4, 3, 2. So 7, 9, 10. The total minimum distance is 10. So this is the shortest tour. So this is what the traveling salesperson problem. See, this is very simple example we did manually easily. But when the number of cities are more and the edges are more, so then it is difficult. Then we need to apply some techniques. So the same traveling salesperson problem can be solved either by applying exhaustive search, that is a brute force technique. There what we will do, we will find all the possibilities, and out of all the possible solution, we are selecting the best one. That is what the brute force. Now the same problem can be solved by using backtracking also, in which in the backtracking we are exploring all the nodes possibilities. Okay, even though we know from here it is not possible, still we find all possibilities again. Feasible and non-feasible, both we will check. But now how branch and bound technique solves? The branch and bound, as the name itself indicates, for every node, okay, for every node we are calculating on bound value. one bound value you are calculating. That bound value may be maximum or it may be minimum. Instead of telling that, see that bound value may be what? Maximum or it may be minimum. Instead of telling maximum, I will say upper bound, and I will say instead of minimum, I will say lower bound. So that means for every node, I am calculating one bound value. That bound value is depending upon the objective of the problem. For some problem, objective is to get minimum value. For example, traveling salesperson, shortest distance. Okay, so the minimum value. For some problem, objective of the problem is maximum. For example, knapsack problem. In knapsack problem, we need to select the item in such a way that we should get maximum profit. So their objective is maximum. So like that, for some problems, objective is maximum. For some problems, objective is minimum. Depending upon the objective of the problem, we are finding the corresponding one bound value we are calculating. Now, whichever the bound value is promising us to give the optimal solution, only that bound value node I am branching. Remaining, I am not at all exploring. Okay, that is called the branching. That means I am branching. That means I am expanding. I am expanding the node which will give us the bound value objective. Otherwise, I am not exploring that node. That's what the branch and bound. Okay, and this branch and bound technique is used to obtain optimal solution. That means for the optimization problems, we apply this branch and bound. Now, hope you people understand what you mean by traveling salesperson problem and what you mean by branch and bound technique. Now, let us take a simple example to find out how to find out the optimal solution, or in this traveling salesperson problem, shortest distance how to calculate by applying branch and bound. Okay. Now, this is the given graph. For this graph, now we need to find what is the shortest distance covered by the salesperson in such a way that he starts from one city and visit all the cities exactly once and has to come back to the same city in a shortest distance. And to solve this, we are applying branch and bound. So in branch and bound, again I am told for each and every node in the state space tree. That means again I am using state space tree to construct, to solve the problem by branch and bound technique. So in the state space tree, for every node we are calculating on bound value. Since here we are finding the shortest distance, here we are calculating lower bound. So I am calculating a lower bound for every node. Okay. Now how to calculate this lower bound? The lower bound is equal to the formula I am writing now. Formula, the lower bound LB. Lower bound is equal to sum of two nearest cities. Sum of two nearest cities of every node. That divided by 2, and that I am taking the upper bound. Because when I am dividing the two integers, I may get fractional part. So I need to either lower bound or the upper. Okay, I need to round it after upper or to lower. So I am going into lower, upper. Okay, so this is what the formula. Just how to calculate lower bound? You find out the two nearest cities of every node and add those. That is what sum of two nearest city of every node divided by 2 and take the upper bound. That's it. You can take lower bound also, not a problem. You take any one bound, fine, not a problem. Okay, this is the only formula. Now, assume I am starting the tour from A. For example, assume I am starting from tour A. So that means now from A I am starting. Now what is the lower bound for this? Okay, lower bound. Now for A, lower bound. Now we find out for each node. For A, which is the two nearest cities, C. From A you can go to B, you can go to C, you can go to D, you can go to E. So which is the nearest one? C. 3, 5, 1, 8. 3, 5, 1, 8. Among which is nearest? 1 and 3. So for A, 1 plus 3. This is the two nearest cities I can reach from A plus, now A is over for every node, for every node. Now A over, now B. For B you can again, from B you can reach to A, C, D, then E. Now from B, 3, this is 6, 7, 9. 3, 6, 7, 9. Which are the two nearest? 3 and 6 is the minimum, 3 and 6 minimum. So I'm taking 3 and 6. Plus, now B is over. Now similarly check for the C. You come in an order. Okay, C. C, 1, 6, 4, 2. 1, 6, 4, 2. Which are the two nearest? 1 and 2 minimum. So I'm taking 1 plus 2. Plus, now C is over. Now check for the D. For D, which are the two nearest cities? C. 3, 4, 5, 7. 3, 4, 5, 7. 3 and 4 is the minimum. So 3 plus 4. Plus, now again last one E. E, 2, 3, 8, 9. So 8, 2, 3, 9. So these 2 and 3 are minimum. So 2 and 3. So this overall I'm adding. So I'm divided by 2. Okay. So divide by 2. So divided by 2. So this is nothing but 1 plus 3, 4. 4 plus 9 plus 3 plus 7 plus 5. This is divided by 2. So 4 plus 9, 13. 16. 16 plus 3, 23. 23 plus 5, 28. 28 by 2, 14. This is my what? Lowest bound. So for A, bound value is 14. So hope you people understood. So for node A, my bound value is what? 14. Okay, this is done. Okay, now I will clear this. Okay, same thing I do. Okay, now what? From A, I started. From A, I found the lower bound. Now what I will do? See, from what are the possibility that from A I can go to where and all? From A I can go to B, or I can go to D, or I can go to C, or I can go to E. Now I'm exploring all possibilities. First, in the first level, I'm exploring all things. That means I can go from A to B, I can go, or I can go from A to C, I can go, or from A to D, I can go, or I can go from A to E also, I can go. Okay, so these are the only possibilities, right? So these are the possibilities. Now I'm checking A to B. That means you fix. Okay, now I'm rewriting the same thing now, just to illustrate, to explain. Same thing. Okay, now what is the meaning? That means if I prefer from A, I'm coming A to B only, A to B. So that means I have to include this edge. A to B have to be there. Okay, remaining whatever. A to B have to use. Now again you check. Now again I need to calculate the bound value for this. Now again start calculating for this one. Okay, calculating for this one. So this is for AB. Okay, for A comma B. Now A to B. A, what are the possibilities? 1 and 3 is the minimum. So this 3 should be included. This 3 should be included. Yes, it is there. So 1 plus 3 only plus this for B. B I should include this 3. And then another next is for B 3, 6, 7, 9, 3 and 6. Same thing. 3 plus 6 plus. Now again, but C, there is no constraint. C, same thing. 1 and 2, same 1 and 2, C. So this is for A, this is for B, C, D, E. Then for B, no constraint, same thing for D. It is 7, 5, 4, 3. So 3 and 4 are minimum. Same thing here also. 3 plus 4 plus E. Again for E, 2, 8, 3, 9, 2 and 3. So this I divide by 2. So now same thing what? Same thing, this is also same value. So again for I will also get here 14. Okay, lower bound is what? 14. So now one option A to B, for that I calculate the bound value. Now suppose if I come from A to C, that means from not here, suppose if I prefer, I will come A to C. What is A to C? 1. That means now this edge you have to include. Okay, obviously this 8 means A to C means now for A. Again you calculate the bound value for this one, A. Okay, now A to C. For A to C also, it remains same because for A, now you have to this edge should be there means 1 and 3 minimum. Same value get 1 and 3. For B, again 3 plus 6, same thing, everything is same. So for this also, I will get 14. Okay, you try like this similarly. Now, suppose if I prefer, instead of going B or C, if I decided from A to D I will come, A to D I will come. So that means I am coming from what? A to D. So what is the edge? This cost 5. So 5. Now you have to include this edge. Either for A or for D, this edge should be there. For A and D. Here the commonly done mistake, students. Okay. So here this edge, that means either A to D or D to A. That means for both A vertex, D vertex, you have to consider. Now see, check. I'll change here only. Okay, A to D, A to D. Okay. Now for A, this edge should be compulsory 5, and next minimum is what? 5 and 1. For A, 1, 8, 5, 3. Among these 4, 5 is compulsory, and next minimum is 1. So 1 plus 5 instead of 3 here. Instead of 3 here, now I am making this as a 5. Now that is the difference. 1 plus, earlier 1 plus 3, now it is 1 plus 5. Now for B, there is no condition. The B may be whatever the minimum. So again B, this edge is not related to B. So B 3 and 6 only. B 3 and 6 only. For C, there is no condition. Again remains same. For D now I have to D to A. That means I have to include this edge. That means this 5. B, this edge should be there, and next minimum is this 3 for 3. So 3 plus 5. So 3 plus 5. Okay. E remains same. Now you add 6. 6 plus 9, 15. 15 plus 3, 18. 18 plus 8, 26. 26 plus 5, 31. 31 by 2, how much? 16.5. That I am making as an upper bound. So I am getting 16. 31 on 31 I got 31 by 2, 15.5. 15.5 I am upper bound into 16. So this is the upper bound for A to D. Now suppose if I choose A to E. So then what? So then I have to prefer what? So instead of this A to E, I need to come A to E. So this A to E I need to come. A to E here, this is 8. This 8 I have to include. Either for A or for E I have to include. So for A, see now again calculate the bound value for this. So for A, 8, 1, 5, 3. So this 8 compulsory. So 8 next minimum is 1, 5, 3, 1. So 1 plus 8. So I am changing for A. It is 1 plus 8. 1 plus 8. Okay, this is for what? A to E. A to E, 1 plus 8. A is over. Next, B. Again, B is not included. So 3 plus 6. 3 plus 6. For C, again not included. This 8 is not related to this one. C, 1 plus 2. This only 2 nearest it is. Now for D. For D again it changes now. For D. Okay, for D. See, the D, 5, 4, 7, 3. Which are minimum? See, D is not related to this edge. So, these 3 and 4 is minimum. So, 3 plus 4. And then now for E. You have to, earlier 2 and 3 was, for actually E is 2 and 3. But this set is compulsory, 8. And another one is 2. So, 2 plus 8. Now we add again. 1 plus 8, 9. 9 plus 9, 18. 18 plus 3, 21. 21 plus 7, 28. 28 plus 10, 38. 38 by 2, 19. So bound value is 19. Now one level over. Now, if we observe from A, possibilities I can go to A to B, A to C, A to D, A to E. Among these 4, which is minimum? These 14 are minimum. So these 2 are ruled out. I am not exploring this, or I am not expanding this one. I am expanding any one of this because both are 14. See why I am see. Whether you go from this place to this place or this place to this place, both are same. Whether go from here to here or here to here, distance is same. So I am expanding any one. So I am not expanding both also. Okay. Now let us see. I expanding this one. I'm branching this one. That's what the branch and bound. I'm not branching the remaining. I'm branching only here. So now I move from A to B. That means this is fixed now. Now what is my decision? My decision is I fix that I am moving from where to where? A to B I fixed. So this 3 is fixed now. This edge. Now I go from there, started from A and then from A I went to B. What are the possibilities? From B I can go to C, or from B I can go to D, or from D I can go to E. That is the possibilities. Okay, so that from A to B I can go to C, A to B to C. Suppose if you are going A to B to C, A to B to C. So B to C at this what? 6 cost is. Okay. Now you find the bound value for this one now. Now find the lower bound for this one. Okay. Now I'm finding for A, B, C, A, comma, B, comma, C for this node. Now I'm finding for A. First A, I have to include these 3, 1 edge. So 2 nearest cities. A is 3, another one is 1. So for A, 1 plus 3 for A. Next, B. There is no option because from A to B and then B to C, that means B, this edge also included, this also included. So these two only I have to use 3 plus 6. Next, for C, now see earlier for C, 2 nearest cities was, this is 1 and 2. This is the 2 nearest. But here I have to use this C, 6. Okay, this edge, B to C. So this 6, next minimum is 1. So 1 plus 6 for C. Next for D, it is not related to these two edges. So D minimum is 3 and 4. So 3 and 4 plus E. For E again is not, these two edges are nowhere related to here. So for E, 2 and 3 is the 2 nearest cities. 2 plus 3. So then sum all these things, divide by 2, take the upper bound. 4 plus 9, 13. 13 plus 7, 20. 27, 32. 32 by 2 is 16. So I got 16 lower bound. Okay, now that means from A to B I went to what? C. Similarly, what is another option? A to B to C I can go. Similarly, I can go to what? A to B to D also I can go. If I go A to B to D, what is this one? Cost is 7. Okay, so now that means A to B to D. Now what is the lower bound for this one? Okay, if I go here like this. Okay, now for A to B to D, A to B to D. Okay, now this we have to include 3. So and then plus 1 as usual. 1 plus 3. 1 plus 3 plus for B. Now B, no option, these two edge only. This B is associated with this edge also, with this edge also. So 3 plus 7 only. 3 plus 7. Next for C. C, it is not at all related. So C, 1 plus 2. Next for D. So D, we have to include this edge. Okay, and the minimum. This is 7. Next minimum is 3. So 3 plus 7 plus E. E is not associated with these two edges. So E, 2 and 3, 2 short nearest cities. Now again add these two and divide by 2. 4, 14, 17, 27, 32, again 16. So again I got here 16. Okay. Now suppose instead of moving from A to B to C or A to B to D, I prefer moving from A to B to E. If I prefer A to B to E, Okay, now B to E, it is what? B to E is what? 9. So this is the edge. Okay. Now what? Now I need to calculate for that one. Okay. Now I will change here only A, B, C, E. See, A, B, C, E. I'm doing, okay, not this one. Wait, I will write once again. Not a problem. What is the 9? Now A to B to E. A to B to E. So for this I need to find what? Lower bound. So A to B to E. Now you check. Now for A, this should be there. Another minimum is 1 only. So 1 plus 3 plus. Now for B, no option. These are the two edges we have to. So 3 plus 9 plus for C. C, it is not related to any of these two edges. So C, 1 plus 2 only. For D, 3 plus 4 only. Next for E, now you have to consider this edge. For E, earlier we have taken two, these are the two, actually these are the two nearest cities, 2 and 3. But this edge you have to take 9. 9 and then next minimum is 2. Okay, so 2 plus 9 and then you add all these things and divide by 2, take the upper bound. 4 plus 12, 16. 16 plus 3, 19. 26. 26 plus 7, 37. 37 by 2. So 37 by 2 means 18.5. That I am taking the upper bound. So that is 19. So that means this is 19 lower bound. Now I expanded only this branch. So these nodes I have not expanded because this is both are same. Now I expanded this. Among these three, this I am not at all expanding because this is what? More than these two lower bound. So now I will try these two, which will get minimum, that I will take. Okay. I need to expand these two. So from A to B to C, that means this is fixed, A to B to C. Now from C, either I can go to D. Okay, suppose if I go from C to D, the next option is nothing. I have to go to E, and then from E, I have to go to what? Back to the starting city A. So from here, A to B to C, if I go to D, like this, if I go to D, this is my 4 value, then there is no option. From D, where you have to go? From D, you have to go to what? E, and then you have to go to A only. Now you calculate directly, no need to calculate lower bound now. Directly call this, okay, from D to E I have to go, from E to A no only I need to go back. Okay, so D to E is 3 and then E to A is 8. Now you count this. 3 plus 6, 9. 9 plus 4, 13. 13 plus 3, 16. 16 plus 8, 24. So the bound value of this is 24. Bound value is what? 24. Okay. Now, this is one possibility. Next. Now, suppose if I am not going to like this, if I am not going like this, that is A to B to C. So A to B to C is fixed because A to B to C, I am expanding this, A to B to C is fixed. Instead of going from C to D, if I decided go from C to E, okay, that is A to B to C to E, then again I don't have any other option. From E, I have to go to what? D, and then from D, I have to go to what? A back. Now, if I go here, C to E is 2, then E to D. E to D is 3, and then D to A is 5. So, this is 5. Now, add all these things. So, 5 plus 3, 8, 14, 16, 19. So, its lower bound is 19. That means, if we go from A to B to C to E, next option from E, D, then back to A. No option. So, these are the two things. Next, now you need to expand this one also. We need to check. Okay, so now from A to B to D, suppose if I fix this one, so what is the meaning? So if A to B to C is fixed, from here A to B to C to E, C to E, and then from E to D. Okay, no, not this. This is already over. Not to expand this one, sorry. A to B to, this is not, if this is fixed, A to B to D, A to B to D, if this is fixed. Next what? Possibility from A to B to D, A to B to D, either I can go to C or I can go to E. Only two options. Okay, now from here. Okay, now if you go for A to B to D to C, A to B to D, A to B to D, then D to C, that means D to C, then there is no option. You have to go from C to E, and then E to A only you have to go. Now if you go like this, so this edge is 4, this edge is 2, this edge is 8. You add this weight. 10, 14, 16, 24. Okay, so now this bound value is also 24. That means if you go from C to what? C to A to B to D, D to C, and then to A. B to C to A to B to D, then E to A. This is the bound 24. Okay, now the last option. Now if we go from A to B to D, A to B to D. This is A to B to D is fixed. A to B to D is fixed. Then from A to B to D, you are going to E. If you are going to E, then there is no other option. You have to go to C, and then you have to go back to A only. That means from C to A only you have to go. So now you add these weights. 3 plus 7, 10, 13, 15, 16, your bound value is 16. Now, out of 4, which is minimum? This is the minimum. So, this is your shortest tour. That means you need to go from A to B, B to D, D to E, E to C, then back to A. Starting and ending of text is same. For this is the illustration. So the cost of this path is 16. So this is the shortest tour. So this is how our branch and bound technique solves the traveling salesperson problem. Okay, hope you people understood. So you take one simple example first, you solve this and you verify, and then take a 5 notes or 6 notes like this. If you have any questions, please write it in the comments. Thank you. Thanks for watching.